Okay, welcome to the second video of 1.2 atomic structure subtopic in topic 1. In this video, we'll be covering 1, 2, 3, fourth box down here. So it's about the atomic number and mass number. They provide information about the numbers of subatomic particles in an atom. Many elements consist of a number of different isotopes. So we'll be talking about isotopes as well, which have different physical properties but the same chemical properties. Interesting, isn't it? And what you need to be able to do after watching this video is to be able to represent isotopes of an element using appropriate notation. All right, let's have a look. Okay, so atoms and isotopes, what do you know about it? Well, you may have seen, well, above you as well, if you look at the periodic table, you can see few numbers are written and they're all consistent with any periodic table that you look at. For example, carbon, that's shown, this way, carbon this way here. You can see the atomic number is at the top here. And the symbol is there, as well as the mass number, atomic mass. Atomic number, what does it show? It shows the number of protons, and in an atom, the positive and negative should be the same, therefore number of electrons as well. So carbon has 6 protons and 6 electrons. C is a symbol, and you would probably see a name if the periodic table was big enough. So you can also see the appropriate spelling as well. And then atomic mass at the bottom is an AM, it's in the unit of AMU, so atomic mass unit. So if you have got what's called 1 mole, that's the number of atoms stuck together, it's like 1 dozen of it. 1 mole, 1 dozen, sort of the same thing. If you manage to collect 1 mole of atoms of carbon together, it will have on average of 12.01 grams. So AMU can be translated as grams per mole as well, grams per mole. Now, this is where you can do question 9 and 10 in Essentials workbook. All right, video-wise, we'll move on. So what information does a mass number provide? I have already mentioned that the number of subatomic particles in an atom. Why does the number have decimal part? Have you thought about it? I also said mass number that's shown is an average mass per mole. Many elements consist of a number of different isotopes. For example, hydrogen atom can be called deuterium if there was an extra neutron. Carbon can be carbon 12, carbon 13, carbon 14, and that's used to do carbon dating technique. Uranium, only certain what's called isotopes with certain number of neutrons can be used for making electricity. So it's important for you to know what isotopes there are and which one can be used. So mass numbers are average of these isotopes. Imagine that you have a class of carbon atoms, and imagine that one of you have got 14 as your mass number, but you're still carbon. There are 2 more people who are not 12. 2 more people, those 2 people may have 13 as their atomic mass. Rest of the class would be carbon with 12 as AMU. If you average the mass of everyone there, you'd probably get 12.01 because there are certain people who have got a bit more mass to it. So that's how the decimal part is included. On average, 12.01 is the mass number for carbon. Isotopes, as I mentioned, they have different physical properties, but the same chemical properties. So for example, if I was talking about deuterium, which is an isotope of hydrogen, they would behave in the same way if you say let it react with oxygen, hydrogen and oxygen, they make water. Deuterium and oxygen, they make heavy water. Yeah, you can make water molecule with a bit heavier mass as well using deuterium. Carbon 14 or carbon 13, they would have very similar or the same chemical properties, but physically speaking, if you could put them together and find the boiling point or melting point, they would be pretty different. They represent isotopes of an element using appropriate notation. How can you do that? Well, we'll probably draw it on the board, or you can do a bit of research, or just look at here and work it out. This diagram shows the notation. So if you have got hydrogen, 1, 1, that's what they say, okay? Think of what they represent to. And deuterium, the one that I kept mentioning, it's still hydrogen, but 2 at the top and 1 at the bottom. What do they mean? And tritium, apparently there's another isotope that's available. And if you look at that, it says H with 3 and 1. What would that mean? Think about it. I'll ask you again. What would those number 1, 2, 3 and 1, 1, 1 mean? Oops. Yeah, it's the last slide here. Use of radioactive isotopes. So this is She connection here. So where do we use isotopes? As I already mentioned, you use carbon 14 and a natural decay of it, which happens as soon as the living organism die. It will eventually become C12 or C13, but it takes a lot of time. Therefore, you can use that technique to measure how old some artifacts are. So geologists and archaeologists, they use this carbon dating technology to figure out when those, say, fossils come from, which era or which year. Radioactive isotopes are also used in radioisotopes in South Australian Health and Medical Research Institutes. By using some radioactive isotopes which have got very short amount of lifetime, I suppose, short life, you can inject it to human body and let the person be radioactive for a while. But what's happening, you can measure where the cancer cells are, or where the clot gauge in the artery are, things like that. So it's used fairly often nowadays in medical field and also agriculture as tracer of where things are stuck or where things are working. Okay. Now, after watching this one, in class, we will be doing page 19 and up to question 11. So ask me if anything didn't make sense, or something that if you had any question that you wanted to ask. All right, thank you for watching. This is the end of second video.